Where is the pointer? Okay. Okay. Hello. First, I would like to thank organizers to give me a possibility to talk here. So I would like to give yet another approach for solving a strong complete limit by the traditional equation. And this approach is somehow dual to one which was proposed Benjamin yesterday. So main goal for this small talk will be to derive the ansatz for strong complete expansion. Actually, this approach is close to be somehow rigorous, but okay, it still have some points, subtle points. Okay, here there are some formulas which are, some formulas here are similar to what I write here. In this talk, I need two setups. First is Zhukovsky map. Many people know, but still I decided to talk about this. Zhukovsky map is a map of type 2 to 1, which takes one point in the circle, one out circle, and maps to the same point on the U space. Inverse of Zhukovsky map is, of course, some double-valued function. And since I like to work with single-valued functions, I precise my sheet by this condition, which gives me a physical sheet. Also, I would like to note that when I precise this condition, inverse Zhukovsky map is the antisymmetric function. The second part of my setup is the introduction of resolvent for fluctuation density in best equation. As I would show in a moment, if I take my physical resolvent in the upper half plane and make analytical continuation in the lower half plane, I will see that this resolvent has such branch cut structure. It was noticed by different people a few times that best equation, which contains dressing phase, after some transformation can be reduced to two equations, but these two equations do not contain a dressing phase. We will also use this transformation, and of course, if we have two equations, we have two functions to determine, and the setup for these two functions are r plus and r minus. R physical is defined like this. So I start from a variant of this equation. So you see that this equation has u and u shifted by e epsilon. As well, here is the rank in integration, and the integration is also shifted. So it's local in this sense also. And what is good here that this kernel is have very simple form. If you look on the left hand side, we see that it's a good idea to introduce so-called we call it them small resolvents, and then left hand side will be simpler. But why I did this? From the structure of kernel, I see that these small resolvents have a good parity because u to minus u correspond to x to minus x, so the resolvents have precise parity. As well, it's very important property that r plus and r minus has the only cut minus 1, 1 on the physical sheet. How we can see this from this equation? The essential part of resolvent is this multiplier. In the denominator, we have y. This is Zhukovsky map of u prime, and it is always bigger than 1. And here we have 1 over x, which is 1 over Zhukovsky map of u. It is 1 over x is always smaller than 1, except on the cut. So except on the cut, we cannot obtain singularity when doing analytical continuation of this function. So we have the only cut. Knowing this, we very quickly reproduce then all the cuts on the physical sheet of big resolvents. So we have this descending structure. It goes to infinity for sure, because just shifted cuts of this R small. It's a good point now to find what are zero modes of our kernels, because knowing zero modes usually helps to solve equation. So our kernel is the following. Contour of integration is denoted by the blue line, and signed f is a resolvent which is shifted by epsilon, the first cut will be below this blue line at the distance epsilon. So here at this region, this function is regular without an analytical. What is good also that in the upper half plane f is also analytical and kernel as well. So it's okay. And green cut corresponds to this Zhukovsky map. So it will be a good idea to go from here to here. When I pass this cut, I can use this relation for region -1, 1, and this relation outside this region. So I end up with two contours of integration. For yellow contour, I have to change y to -y, and for brown one, okay, here everything is analytic, so I can close this brown contour again to this -1 part. So I end up with the following: k plus acting on f give us the following integration. And I will take its definition of k plus now. What is very nice that these terms can be combined to very simple form. And if I want to find k plus f equals 0, then of course this will be 0 also. And from this equation, I easily integrate rid of the function. What equation should I function f in order to be 0 mod? This is the equation. This equation holds, of course, on the interval -1, 1, and actually, it is not, if we analytically continue this equation, it doesn't mean exactly condition of parity. If, for example, if it's u, it's -u. If we analytically continue u here, and f has somewhere cut, not exactly here, but probably below, this contour will cross this cut, and this relation gives us a relation between function of different cuts on different sheets. Okay, any questions at this moment? Okay, now I would like to show how we can solve this equation, and we use a trick introduced in BKK that up to this, with this substitution, we obtain very simple equations. I would like to notice that I can do this only because of these projective properties of the kernel. I apply k plus and k minus to this equation, obtain this. But the point when I apply this, I lose a lot of information from this equation. So this means that this equation has much more solutions because there are many 0 modes of k plus, k minus. And in order to restore a good solution, we have to use analytical properties which come from this equation. But still, we can solve these equations. So it's very simple. We just note that k plus 1 equals to this. So we can put it inside. We have two homogeneous equations. They give this solution. And okay, it's probably the main formula of this talk that any function which satisfies this condition solve this equation. Okay, I also will remark that up to now everything was perturbatively, it was true even for finite epsilon, and only now, after all this stuff, I will go to perturbative limit. So I remind you what is big gammas, what are small r's, and so I can express big gammas through the small r's. And I see that in principle gamma minus and gamma plus have no any parity properties. But if I take even part of gamma minus, I see this is equal to some periodical function with period I epsilon. And when I epsilon goes to 0, this means the periodical function has a very small period, then it's constant. And R plus, I know that is decreased at infinity, so this constant is 0. If you don't believe, you can make a Poisson's summation. You see that 0 plus non-perturbative corrections. So important statement is that gamma minus and gamma plus have the parity. Gamma minus is odd, gamma plus is even, only perturbatively. But perturbatively, we can use these properties. And perturbatively, we can come from this equation to the set of these two equations. What this equation do mean? Okay, when I start from above the cut for gamma plus, I go through the cut, I get gamma minus. When I go from above the cut for gamma minus, I get minus gamma plus. When I start from minus gamma plus, I get minus gamma minus. When I start from minus gamma minus, I get gamma plus. This means very simple fact that gamma plus and gamma minus are branches of the same analytical function, which has four-sheeted Riemann surface. And if you, it's very simple to solve this Riemann-Hubert problem explicitly. This is this function. This is Zhukovsky map, so it has another square root here. And this function g is some analytical function. But from the very beginning, I know a lot about these big gammas, and I know that g should be analytical everywhere except -1 and 1. And g should decrease at infinity. So this big G is this function. Now it's a very nice property. At the leading order, in order this to decrease at infinity, I have to put big G equals to I epsilon. And when I do this, I obtain a well-known Arbeck solution.
Why G can have only power singularity? Why can't it have essential singularity in one?
Because it's an analytical function, meromorphic if you want. So you see that we can obtain this solution in a very simple way. As well, we can write write ansatz which appeared in Becker work.
Sorry, do you have any idea what the specific meaning of this block?
What do you mean exactly?
You say that these labels are based on the scaling of the space.
Yes. So I will comment at the end of the talk. I will comment. So if we just sum over all possible solutions, we obtain an arbitrary solution for gamma plus gamma minus. Now here is a very interesting fact that for when we have in denominator power 2p, we have the lowest power of epsilon here p. Right? So I just want to give you a very simple example. I just take some toy model function, not really related to the problem, but somehow similar. And I see this function is a very nice function. It is integrable, and for epsilon finite, a u equals 0 is a good point. But when I try make expansion over powers of epsilon, I see that my expansion contains also singularities. And except the first order of this series, all of these are not integrable. But order of singularity is governed by the order of perturbation theory. Actually, the point that when u equals 0, this square root of epsilon is not an analytical function, and we cannot, in the sense that it cannot be expanded in the Taylor series. Here we have the same situation. Actually, this is 1 minus x squared to the power 2 is equal to 1 minus u here. So it's the same property actually. X equal to plus minus 1 is a bad point to make this expansion. Now I just make a little comment which is rather nice, that even we still don't know these coefficients, but even if we don't know them, we can calculate density in this fluctuation density in giant magnet region. Actually, what to do is just we express our physical through gamma minus gamma plus, and we see that using this equation and using definition of density, we see when we calculate this term just cancels. So that's it. In perturbation, in perturbative expansion, without non-perturbative corrections, in this region we have fluctuation density is constant to all orders, and as well this means that total density is 0. Now I will go close to the work of BKK and explain somehow what is the idea to fix the coefficients, but still there are some points. So the idea is the following. Let us consider this small r function which can be expressed from gamma in this form. I told you already that r plus minus have the only cut. have the only cut. But the point, this cut, I can prove we can prove that this cut can be resolved by Joukowsky map. And even we know a lot about analytical structure of f of x in the Joukowsky space. Actually, it's analytical everywhere outside, it's analytical on the contour, and it has branch points of order 2 here on these lines, which condense at 0. This means that if we want to expand R plus of x at infinity, then this series will be convergent with finite radius of convergentity defined by this first cut point. Since I can calculate where it's situated, I know that this coefficient have to decrease as this to have this radius of convergence. Okay, now it's it's almost the same, like in BKK work. So I know expression from this formula we can read that R plus of x has the following expansion, and if we want to expand this expression at x goes to infinity, obtain this series for coefficient of k, and for k big it looks like this. So if we want to use this property for k big, if we want to go to epsilon goes to the limit, we see from this construction, from this, we see that it's very natural to introduce BKK double scaling, which was told yesterday. We will take some function which decrease at infinity as exponential of minus square root. And then, okay, the arguments to make BKK quantization condition, okay, it's exactly the same. So we make Laplace transform and say for RAS bigger than 0, it should not have singularities. And some structure for S goes to infinity. But okay, I have two more notions that give us that do not give us possibility to exactly fix this coefficient, but in the work of BKK, they somehow guessed by minimum satisfaction of these conditions. Okay, the last comment what I want to know that I would like to compare BKK double scaling with near flat space double scaling. By near flat space limit, I call point x equal 1 or minus 1. Okay, you see this expansion suppose that it's a good idea to introduce double scale variable omega, and if we compare this series with BKK double series, we see that coefficients are quite related. So these limits have a nice relation between each other. It will be nice. I mean, analytical properties from here can go here and vice versa, and it should be nice too. And I just want to note here that if we calculate derivative over u which acts on this function, if we go through these conditions, we obtain that at the leading order, these derivatives come to integration over parameter z in double scaling, which actually helps, for example, calculate these expressions in Laplace transform. Okay, now come to discussion what we have. We have the perturbative, now the perturbative Van-Alpha solution is nicely understood. Okay, and actually the point that these coefficients, okay, they are known already by this work, but I would like to note that the procedure need two inputs, analytical structure of R plus minus, and also some special pole zero structure of f of s, which should be still understood, but there is a guess check numerically how it should look like. As well, it's tempting to go to non-perturbative limit. Okay, I showed you that it's obvious. I just subtracted some non-perturbative terms that they're present on perturbative terms. And I believe also that understanding of this structure is important. Actually, I have to comment why. This naive epsilon expansion actually is good everywhere except near flat space limit. And the point if we expand like this, all cuts they collapse to one cut, and actually we lose a lot of information and we cannot restore really nothing. But okay, actually what really is needed to do is to go to double scaling, because in double scaling cuts they do not collapse, they're still present, and from there read the quantization conditions. I mean, and somehow f of s should encode this all cut structure in itself. As well, I would like to note that we know a lot about analytical structure of exact solution by this functional relation and by some others. Okay, I should of course help. Okay, and I would like to replace somehow with this formula, and okay, I have still hope that probably there is exact solution. Okay, before I end, I just will comment Matthias' question. Okay, technically it's like this. Zhukovsky variables plus minus introduced by Bizert can be parameterized as following. This is moment which comes to beta equations. Condition written in this form like sinh beta over 2, sin p over 2, proportional to 1 over g. Now I see that I go to g big. This means they can mean the following: either p proportional to 1 over g. This will be plane wave limit. Either and this limit beta proportional to 1. Either p proportional to 1 and beta proportional to 1 over g. This will correspond to giant magnet region. And there is a near plate space limit where we have this. Okay, of course we can have other situation with fractional powers, but I mean it's hard to imagine how to manage them. I mean this is arguments why I called these limits like this. Okay, this point corresponds to x equal to 1 or minus 1. Okay, thank you.
Could just say again what will be the place on your solution when the perturbative correction will intervene?
I mean, I know the play where I just subtract some part of the perturbative corrections.
Because the problem is that at the end we know the series will be Borel non-summable.
Yeah.
Same time with the equation, the PS equation, they give you the number, right? The number means that the solution, the equation is correct in the sense that we give a value of g, it gives you the number.
Yeah.
Now you compare the number with Borel non-summable series. So if you want to make meaning of this Borel non-summable series, you have to do two procedures: to regularize the series and to add perturbative correction to the top. Therefore, this construction should take care simultaneously of two things: regularize perturbative expansion plus add the perturbative correction as well. So at which point I have to look at your solution to see where this procedure will be implemented.
I mean, in this talk I just mentioned that okay, I cannot answer completely to the equation. I want to say that in this talk I just mentioned that obviously that gamma minus contains this part which is non-perturbative.
But this will be, if it's not zero, what will appear on the right hand side? It will be something that you will put by the hand, or it will be something which will be deduced from the equation. Defined by the equation. So, but what would be the additional condition you have to impose to define what will appear on the right hand side from the equation?
No, of course I cannot clearly answer the question. That I know that I know this analytical structure. I mean, I just can play with this actually.
Wait, do you believe that this picture is sufficient and necessary condition for constructing the exact solution for the equation?
Yes, I believe.
That's fine.